All right. We are taking what we've learned about integrals and area and expanding that to help us figure out the volume. So here is kind of a strange 3D shape, and maybe it could even look like a bone or something. But what we want to do is be able to, first of all, picture a cross section of that 3D shape. Cross section would be if you cut that shape and stared into where you cut it, what shape would that be? So if we cut a sphere down the middle and stared into it, what shape would we see? We would see a circle. If we cut a Snicker bar down the middle and stared into it, what shape would we see? Roughly a rectangle. So those are called cross sections. All right. And volume, you could consider volume as like area that is extended into a third dimension. So if we can figure out the area of the cross section and then extend that area in another dimension, then we can create volume that way. All right, so the volume of like this shape here, let's say it's like this. All right, and then if we extend it that way, and let's just say we extend it this far. So now we have this like a solid right here, a three-dimensional shape right here of some width delta x, let's say. So we have this area, and so if you want to get volume, volume would simply be the area, let's say as a function of x, times delta x. And that would give us the volume of this piece. The way that it's explained here in the book, volume equals the area times the height, or you can say the area times the length, or the area times however much is extended. So the area times the extension, let's say it like that. That gives us volume. So the trick is going to be, if we're going to use integrals to help us figure out this volume, we've got to integrate with a particular variable. So that could be y, or that could be x, or whatever, but we got to get it in terms of a consistent variable. So like for this shape here, it would, since this is going from A to B on the x-axis, we would integrate this cross-sectional area with respect to x. So we would want to get the area in terms of x so that we can do an integral. All right, so let's keep going here. All right, this is kind of showing the same thing. Kind of like we did with the curve, and you had, rectangles that were fitting into that curve to approximate the area of the curve. Now instead of just two-dimensional rectangles, we're getting three-dimensional slices, almost like a slice of bread. Like imagine this was kind of a weirdly shaped loaf of bread, and we're getting a slice of bread from that. That slice of bread has a small volume associated with it. Well, if it's a finite number of those slices, it's kind of like this. Like if we did a finite number of rectangles, then the area would be approximately the sum of all the areas of those little rectangles. And if this was a finite number of slices, then the volume of this would be approximately equal to these slices. But as we fit more and more slices, you can kind of see where this is going, we're going to fit an infinite number of slices into there that are all going to be infinitely small. All right, let's see how maybe we could visualize that. Let's say we have this, and then we have this. You can see that there's definitely a big difference between the area here and the area here. But if we're here and here, the area is not as much because we're closer together. And if we get even closer, then the area would be even closer to being the same at both ends of that slice. And so if we get infinitely close, then the area is the exact same cross-section because it's like at one single plane instead of two different faces of that slice of bread, because the slice of bread would be infinitely thin, so it would just be one face of that slice of bread. All right, so the volume of the kth slice is equal to the area of the kth slice times the delta x, which is like the thickness of that slice. Well, coming here, we have the volume is approximately equal to all the little volumes added together, and all those little volumes are the area of the face of the slice times the thickness of the slice. Area times the thickness. Okay. Well, you get down here, and we are making the norm of the partition. In other words, the thickness of the slices. The slices, in the language of calculus, the slices we're putting an infinite number in there, but they don't even have to be the same, they don't have to be consistent widths. Well, what we say is that the widest one, the norm is the widest one, and if you make that go to 0, then if the widest one goes to 0, then all the others would have to go to 0 too, by definition. So that's when we get there. And if that's the case, then we're going to have an infinite number of slices. And then when we have that, as we learned in the previous section, that becomes the integral. So if we integrate the area over the length of the integral from A to B, then we are going to get volume. It's like the cross-sectional area is marching down the line from A to B, creating volume as it goes. And the integral accumulates all that for us. So here's the kind of a definition, a more formal definition of volume of a solid with a cross-sectional area A of x. Notice that the cross-sectional area is not a constant. It is a function of x. In other words, it can change as x changes. And that's how we can really do lots of different looking kinds of solids that way. So here is a kind of a good step-by-step process. First, you want to sketch the solid and a typical cross-section of it, and then find the formula for A of x. That's the cross-sectional area in terms of x. Find the limits of integration, which is sometimes easy. Sometimes you got to do a little bit of math to figure out the limits of integration. And then finally, once you've got the area expression, you've got limits of integration, then you can integrate that thing and find the volume. So here's example 1. A pyramid 3 meters high has a square base that is 3 meters on a side. The cross section of the pyramid perpendicular to the altitude x meters down from the vertex is a square x meters on the side. Find the volume of the pyramid. We're going to follow those steps. First we sketch it, and here's a good sketch. So notice that it is laying the pyramid on its side down the x-axis, so that when you're at an x value of 3, you have a square cross-sectional area with that square having a side length of 3. And it comes to a point at the origin where you have a square of side length 0. In other words, not a square, but a point. And if you're at 2, you have a square cross-sectional area of side length 2. If you're at 1, you have a square cross-section of side length 1. If you're at 0.8, you have a cross-section that is a square of side length 0.8. All right, so what we want to do is find a function for the area of a cross-section in terms of x, and that won't be hard to do here. First of all, what is the area of a square? Where for a rectangle, it's length times width. But for a square, the length and the width are the same thing. So it's like L times L, or W times W, or let's just say a side times side, or S squared. Okay? Well, as we go down the x-axis, wherever we end up, if we call that x, then the cross-section is a square of side length x. So what is the area of that square? If the side length is x, then the area of that square is x squared. It's x times x. So the cross-sectional area as a function of x is x squared. And that cross-section changes as it moves down the x-axis from smaller to larger. So, all we have to do is integrate from whatever the limits of integration are for this problem. We can see just kind of from the figure and from the description of the problem that cross-sectional area is marching down the x-axis starting at 0 until it gets to 3. And that's where it stops. So 0 to 3 would be the limits of integration. And it's x squared dx. And so all we have to do is integrate that using the power rule, as we know how to do. That's going to be raise it up by 1, that's x cubed, and then divide it by the new exponent, so 1/3 x cubed, or x cubed over 3, whatever you want to say. And that's from 0 to 3. So plug 3 in, we get 1/3 times 27 minus 1/3 times 0. And so that's going to be 27 over 3, which equals 9. 9 units cubed, or 9 meters cubed if the units are meters here. Just to make this more general for you, maybe you can appreciate this even more. If this pyramid here were instead a rectangular prism, or a square prism, if this square were extended straight instead of coming to a point, so if this was a straight extension instead of an extension coming to a point, what would be the volume of that? It would be the area of that square times the extension. It would be length times width times depth, I guess you could say. And the depth here is also 3. So it's 3 times 3 times 3, which is 27. All right. It is always going to be, if you have a prism that instead of extending straight comes to a point, it's always going to be 1/3 of the area of the prism volume. So in other words, you could take the volume of this pyramid and fit 3 of the volumes of that pyramid into the one that would be extended straight. All right, example 2. A curved wedge is cut from a circular cylinder of radius 3 by 2 planes. One plane is perpendicular to the axis of the cylinder. The second plane crosses the first plane at a 45-degree angle at the center of the cylinder. Find the volume of this wedge. So here's a good picture of this wedge thing. So if you, and here's what's kind of interesting to think about. If you were to cut this wedge, we have to figure out what shape we would be staring at. If you cut this wedge and stare into it, what two-dimensional shape are you staring at? It kind of shows you here in this picture, but it might not be easy if you didn't have the picture there. But obviously, what shape is that? It's a rectangle. All right, so we're going to be, the area that we're going to be integrating is an area of a rectangle, but the rectangle changes. The area, the rectangle's dimensions are changing as x changes. It starts out at an infinitely long, a long but infinitely skinny rectangle with no area here, one that's at 0, so in other words, on the y-axis. But as you increase x, that rectangle is becoming taller, and until it gets all the way to 3 here. And so the area is getting larger until it gets to 3. All right. All right. So, how do we know? How can we know how this area of this rectangle is changing as we go down the x-axis? Well, first of all, what is the length? You know, the area of a rectangle is length times width, right? So we got to figure out, first of all, what is the length? How does the length change as x changes? Well, down here is this length. Up here is this length. So you can tell the length is changing. So how is it changing? Can we get some kind of expression that says that? Well, what if it was this curve minus this curve? Because this curve is a semicircle. This curve is another semicircle. All right. This curve, the equation for this one, and we're told that this is a circle of radius 3. So remember, for a circle, it's x minus h squared plus y minus k squared equals r squared. That's the standard form for the equation of a circle, where h and k are the center, the coordinates of the center of the circle, and r is the radius. Well, for our circle, what is the center? It's just 0, 0. So h and k are just 0 and 0. So this would just be x squared plus y squared equals, what is my radius? It actually tells me that in the problem. They're going to show a radius 3. All right, so equals 9. That is the equation of this circle, of the full circle. But you know, a circle is not a function. We need an integrable function. So we want to get it in terms of x. So I'm going to solve for y. I'm going to get y by itself and make it be in terms of x. So it would just be y. So I can say y squared equals 9 minus x squared. And then take the square root of both sides. And I would get y equals plus or minus the square root of 9 minus x squared. Which means the top half of this cylinder, the top half of this circle, the semicircle up here, is the square root of 9 minus x squared. And the bottom half of that circle, so the semicircle that's down here, is negative square root of 9 minus x squared. Are you with that so far? Which means the lengths of these rectangles as we go down the x-axis is the difference between the top half and the bottom half. It's this height minus this height. So it is this minus this. Let me just write that. It's the square root of 9 minus x squared minus negative square root of 9 minus x squared. And what does minus and negative become? Plus. So it's the square root of 9 minus x squared plus the square root of 9 minus x squared, which is what? What's one thingamajigger plus another thingamajigger? Two thingamajiggers. So it is 2 square root of 9 minus x squared. 2 square root of 9 minus x squared. What does that give us? That gives us the length of the rectangles as a function of x. The length of the rectangles are changing as x changes, but it changes according to this equation. So if we know what x is, we know this right here. We know the length of that rectangle. Okay, so far we know something really important that we need to know about getting. We're trying to get an equation or an expression for the area of this rectangle that is a typical cross section of this shape. So far we have half of it. We have the length. What are we missing? The width, and we can say width or we can say height, whichever one you would call it. We're missing this dimension, right? If we could know that, if we could have an expression for that in terms of x, we'd be well on our way. Well, how can we get that? According to the description of the problem, it says the second plane crosses the first plane at a 45-degree angle at the cylinder of the cylinder. So that's this plane right here is crossing the XY plane at a 45-degree angle. It's crossing it at this angle right here, which is 45 degrees. What does that tell us? That tells us that the height of this rectangle goes all the way up to there. And so since it's a 45-degree angle, I just use some good geometry and tree kind of knowledge here, that if I'm x away from the origin here, then that means, according to the geometry of this right triangle here, and that's a 45-degree angle, that means it's a 45, 45, 98 triangle, which means this also has to be x this way. If these two angles are the same, then these two side lengths have to be the same. So if I'm x down the x-axis, then that means the height of that rectangle is also x that way, because of the geometry of it. So now I know the height. I have an expression for the length. This is the length, and x is the height. So here we go. The cross-sectional area of that shape as a function of x is the height times the length or width, whatever you want to call it. And we know that the height we just said is x. That's the height. And the length we just said is 2 times the square root of 9 minus x squared. And you just, little simplification there, just multiply the x with the 2. So this is a good expression for the area of that cross-sectional rectangle as a function of x. And if we have it as a function of x, all we got to do is take the integral down the x-axis from where it starts to where it stops, and that gives us the volume. So it is the area of this rectangle as a function of x as x goes all the way from 0 to 3. And as that happens, that area is changing, and we're multiplying it by the distance over which it changes. And an area times the distance gives us volume. And so now all that's left is to do the integral of this thing. So doing the integral, we guys got to remember our integration tricks and skills. It's not immediately clear to me how to do that integral. So I'm thinking, okay, what trick could I use? First thing I would think about is substitution. And I'm looking at here, I'm saying, is the derivative of that going to give me something that can cancel out with that? And yes, it will. Because the derivative of this would be a 2x. And that x can cancel with that x. That's going to be a good thing to do the integral. So if I let u be the thing inside of the square root of 9 minus x squared, then du dx is going to be what? What is du dx for this? In other words, the derivative. Negative 2x. Yep. Negative 2x. So then, if I solve for dx, du equals negative 2x dx, then du over negative 2x equals dx. And so I substitute that in for the dx. I substitute just u in for the 9 minus x squared, and that would give me the integral of 2x times u to the 1/2 times du over negative 2x. And that 2x and that 2x can cancel. The negative I can move outside, so it becomes negative integral of u to the 1/2 du. And I know that you can integrate that with power rule, which is what they do here. They went ahead and substituted 9 minus x squared back in for u. So power rule u to the 1/2, we increase that by 1, it becomes u to the 3/2 over 3/2, or in other words, times 2/3, and that's where you get what they've got there. Heck of a problem, huh? These problems are all kind of like, wow, kind of problems. So that means there shouldn't be many of them. All right, here is an interesting principle. I don't know how to say this man's name. Cavalieri's principle says that solids with equal altitudes and identical cross-sectional areas at each height have the same volume. So this straight cylinder and this kind of curved cylinder have the same volume if they have the same altitude and if they have the same cross-sectional area at every level. And notice what it says. It says this can be illustrated with a stack of coins. If you have a stack of coins going straight up, and then you kind of push them a little bit in the middle where they're kind of jutting out a little, it's still going to have the same volume because it's still the same amount of coins, and each one of those little coins has the same volume it had before. You kind of shift it. But this also follows immediately from the definition of volume that we have in calculus, because the cross-sectional area as a function of x and the integral a to b are the same for both solids, so they'd be the same integral. All right. The next method, so the first method we learned is the slicing method. All right. The next method we're going to be learn is going to be called the disk method. The disk method, and then comes the washer method, and they're both very similar. The solid generated by rotating or revolving a plane region about an axis in its plane is called a solid of revolution. To find the volume of a solid like the one shown in figure 6.8, so here is this figure 6.8, we need only observe that the cross-sectional area A of x is the area of a disk of radius r of x, the distance of the planar region's boundary from the axis of revolution. The area is then, what's the area of a circle, Carly? Pi r squared. Pi times the radius squared. But here, in this case, the radius of the circle is changing. And it's changing. If we can have it change according to a definition that includes x in it, then we're going to be able to do the integral to find the volume. So, notice this it's this interesting curve right here. But you're taking that curve and you are revolving it around the x-axis. So now you have a solid like this. So if you were to cut right here, what shape would you see? A circle. Yep. Because everything is revolving around a central axis, which means all the points are the same distance from the center at a particular cross section. So if that's the case, then our area, our cross sectional area, is going to be pi r squared because it's a circle. We need to get a formula for r in terms of x. So what is r? All right, this curve right here is y equals the square root of x. So the distance that this thing is from the x-axis, and the x-axis is the center of rotation, changes, and it's the y-coordinate of this curve, and the y-coordinate is given by a function of x. It's the square root of x. So the radius then, the radius of that circle, is the square root of x. So the area would be pi times the square root of x squared. That's the area as a function of x. The area of every cross section is just going to be pi times the square root of x squared, because it's pi r squared. And that simplifies down to just pi x. So we would integrate that. We would integrate pi x from 0 to what? In this case here, according to this figure. That cross section is marching down the x-axis. Yes, from 0 to 4. From 0 to 4. That circle, that circular cross section, is marching down this x-axis from 0 to 4, creating volume as it goes. And that's what that integral tells us. Dx. All right. That would give us the answer. All right. So, easy to do the power rule there. Pi x squared over 2 from 0 to 4. And we plug the 4 in, and we get 16 pi over 2. So that's 8 pi. Plug the 0 in, we get 0. So I think it's just going to be 8 pi. Cubic units. Can I erase this? And that is what we see when we look at the book, continuing on with that word, 8 pi. All right, let's look at example 5. The circle, x squared plus y squared equals a squared, is rotated about the x-axis to generate a sphere. So if you take a circle and you revolve it, you rotate it, and then it's making a sphere, right? Everybody can kind of visualize that, hopefully. Find its volume. All right, so this is kind of how I'm thinking about it. All right, this is x, y. So this thing is revolving around like that. And that's a pretty ugly sphere, but it's something like that. So I'm taking this, I'm just going to say, I'm going to take this semicircle and revolve it 360 degrees around the x-axis. Because it doesn't matter if I revolve this semicircle or if I revolve the whole circle, I'm still creating a sphere. So what is the equation of that semicircle in terms of x? I could just say, so normally it would be x squared plus y squared equals a squared or r squared or whatever you want to say. A being radius. So if I solve for y, what would it be? Move the x squared over, take the square root of both sides, plus or minus the square root of a squared minus x squared. But if it's just the top half, then it's just the positive one. So it's the square root of a squared minus x squared. All right? And so that then is the radius. That then is the radius that is revolving around this x-axis. And that radius is obviously changing, right? It's really small here, but it comes up farther as we go and then gets smaller again. So, but the radius is going to be this. It's going to be the y-coordinate of all these points. And the y-coordinate of all these points is given in terms of the x-coordinate by this expression. So remember, pi r squared it gives us the area as a function of x, where I need to get r as a expression in x. So in this case, it would be pi times the square root of a minus x squared squared. So now it's just going to be the integral of that. I may go ahead and cancel that out. So it's just going to be pi a minus pi x squared. From what to what, though? It goes from here on the x-axis to here on the x-axis. So what is that? This is a semicircle of radius A. A is the radius of this semicircle. Everywhere it has a radius of A. So then now, can you tell me what this is and this is? And I don't want a number. I can't have, you can give me a letter. What is this value on the x-axis? negative a. This is negative a. That's what that value is. And what is this value? Positive a. So then my integral goes from negative a to positive a on the x-axis. And a is not a variable, it's a constant. It's a general constant. So I don't have to treat a as a variable here. It's just like a number. So if I integrate this thing, if I integrate this term, that's just a number. Pi a is just a number. So what's the antiderivative of a number? Like what's the antiderivative of 3 with respect to x? 3x. So what's the integral of pi a with respect to x? Pi ax. Pi ax. What's the integral of pi x squared with respect to x? Pi x to the third over 3. Can I follow that? The integral of this, you just increase the exponent by 1 and divide by the new exponent. So it's pi x cubed over 3. And now I'm doing that from negative a to a. That means I'm plugging a into x and then negative a into x and taking the difference. So I need some room. I don't have a whole lot of room. That's going to be pi a times a minus pi over 3 a cubed minus pi a times negative a minus pi over 3 times negative a cubed. So what would that be? That would be pi a squared minus pi over 3 a cubed. And this will be negative pi a squared. That's going to be plus pi over 3 a cubed. I've got a minus in front of that whole thing. That's going to be plus pi a squared minus pi over 3a cubed. So now if I combine like terms, I just combine those two, and I get 2 pi a squared minus 2 thirds pi a cubed. All right, I see a small mistake in my work. When I was here, I said that radius is the square root of a squared minus a squared, but when I wrote it here, I just wrote it as a minus a squared. So I have a little mistake there. It should be an a squared. So that should be an a squared. An a squared there too. Which would make this be an a squared and this be an a squared. Which would make some things different here. So now that would be, redo that little part there. That would be pi a cubed minus pi over 3 a cubed. This would be negative pi a cubed 2 pi a cubed minus 2/3 pi a cubed. So then what is 2 minus 2/3? That is 1 1/3, right? So 1 1/3 or 4/3 pi a cubed. And this would give us an expression for the volume of a cylinder created by revolving the circle x squared plus y squared equals a squared 360 degrees. 4/3 pi a cubed. And actually, the volume of a cylinder, the volume of a sphere in general, the volume of a sphere is equal to 4/3 pi r cubed. That is the formula for the volume of a sphere. And that's exactly what we got. So the neat thing about that problem was that we were just able to prove or to derive the formula of a sphere. This is how the formula of a sphere is created. Can I erase this? All right, take a look at example 6. Find the volume of the solid generated by revolving the region bounded by y equals the square root of x. So here is y equals the square root of x. And the lines y equals 1. What is y equals 1? That's a horizontal line crossing the y-axis at 1. So it's this line right here. And the line x equals 4. That is the vertical line crossing the x-axis at 4. So we're taking this region right here then. Taking that region right there. And we're revolving it what? About the line y equals 1. So we're revolving it this way. We're revolving it around that. So all we need it's pi. The area as a function of x is equal to pi times the radius as a function of x squared. So we just need the radius as a function of x. What is the radius? The radius that is revolving around that thing is this distance right here. That is the radius. So what is that? What is this distance right here? It's this y-coordinate minus this y-coordinate. Right? It's this y-coordinate minus this y-coordinate. That is that distance. The difference in those two y-coordinates. But we want those y-coordinates in terms of what? X. So then this y-coordinate, as far as x is concerned, is that y-coordinate is the square root of x. What is this y-coordinate? Just 1. It is just 1. So the difference then is the square root of x minus 1. That is a function of x for the radius. Notice how that changes as x changes. So the area as a function of x for every cross-sectional circle there is pi times the square root of x minus 1 squared. Next, so I know that I'm integrating that. But what am I missing? What else do I need to be able to do that in? The limits of integration. I'm missing the limits. So what are the limits of integration? What, in other words, where down the x-axis is that radius marching from and to for that region? 0 to 4 is a great guess. It's the second best guess in the world. Yes. It's from here to here. And it doesn't start at 0 because that's not where the region is bounding. The bounding begins here and it ends here on the x-axis. So we first need to figure out what is this point right here. We kind of already know that this is the point 4. And this drawing is showing us that that's 1. But what if the drawing wasn't showing us that? It would just be where that curve crosses that line. So it's where the square root of x crosses 1. So you set them equal and you solve it. Square both sides, x equals 1. So it's from 1 to 4. All right, this right here shows the steps for completing that integral. All they're doing is they're taking the square root of x minus 1 and they're multiplying it by itself. So they're expanding that, boiling it out, and they get this. And once you get that, then you can just do the power rule for each term. So it's not that bad. Let me also just say, on these, you could also, just perhaps just do it in your calculator. Like, you've gotten a lot of practice at integrating stuff. So if you just do some of these in your calculator, especially since the hard part of this is setting them up. If you get them set up, you need to get most of the credit of the problem anyway. But what you could do is just type this in. So second pi times the square root of x minus 1 squared. And we want to see that thing from 1 to 4. So I'm just going to set my window from like 0 to 6 so I can see it. And my y probably needs to go from like, I don't know. Let's try 0 to like 20 and just see what happens. See if that fits it in the window. I graph it. And it does seem to fit in the window pretty well. Let me make the y min -1. Yeah. So this is what that thing looks like, and we're integrating that. So I hit second calc, and I do option 7. That gives me the integral of f of x. Option 7. And I can type in a lower limit and an upper limit. My lower limit's 1. My upper limit is 4. And it tells me the answer. Look here. 3.6651914. But what if you were in Math Excel and you had to give your answer as a exact answer using pi or radicals as needed? Like this is what 7 pi over 6 is as a decimal. So if that was the case, I would probably just leave the pi out of that integral and do the integral that way. And it gives me 1.166667. Now because it's a repeating decimal, that's a fraction. I can write that as a fraction. So 1.16667. I just need to figure out what is that as a fraction, and then put a pi with it. and 1.16667 is 7/6. And then just put a pi with it, because just remembering that we left pi out of it, so that we could put pi in there as part of our answer. Does that make sense? All right, example 7 shows us one where we are doing an extremely similar thing, but we're going to do it in terms of y instead of in terms of x. It would be simpler to do this region revolved around the y-axis that way instead of doing it according to x. It would just make it way more complicated to try to do that according to x. Okay, so it says find the volume of the solid generated by revolving the region between the y-axis and the curve x equals 2 over y. So look, my equation is given by x equals something in terms of y instead of y equals something in terms of x. And we're revolving it about the y-axis. So we got this curve right here. And that curve is x equals 2y. And we're revolving that thing around the y-axis. So it's going like that. So what is the radius then? What is this? This is the thing that's getting revolved. This is the thing that's creating that circle as it gets revolved. So I need to figure out what that radius is in terms of y. R as a function of y. And that distance, it already gives me that. It is the x-coordinate of that curve. And the x-coordinate of that curve is 2 over y. So then it's going to be pi, the area as a function of y is equal to pi times r as a function of y squared, which in this case is equal to pi times 2 over y squared. And I'm integrating that along. Notice this thing is not marching along the x-axis. This circular cross-section is marching up the y-axis. And it's doing it, it's starting where? It's starting right here at 1 and going to 4. So it's the integral from 1 to 4 of pi times 2 over y squared dy. And then you just do your same stuff, do your same integration techniques. In fact, if you did it in your calculator, you can just put that as an x in your graph. And the calculator doesn't care if it's an x or a y, and it can give you the right answer like that. If you were doing it by hand, you would just rewrite this as pi integral of 1/4 of 2 y to the negative 2 dy, and then do the power rule. So it would become, 2 y to the negative 1 over negative 1, and you do it. Okay. All right. This is the last big concept for this section. So far, we've learned to do volumes by slices, and we learned to do them by disks of solids of revolution. When do you use which? You use slices when the cross sections are like rectangles usually. And you use solids of revolution when the cross sections, well, it tells you when it's revolved around the x-axis. That's when you know to do it. But usually those cross sections are circles. I mean, they're always circles. This next one is called the washer method. You could also call it the donut method. So instead of being a disc that is a full circle, it's a circle with a hole in it. The cross sections are circles with a center of some sort cut out. So you can illustrate that here. So if you have if you have this weird curve and this weird curve, and you're making a region out of that, and you're then revolving that region about the x-axis. But it's because it doesn't go all the way to the x-axis, it's a hole cut out of that thing. Something like that. And that's how you get this fancy green lampshade right here. You didn't know lampshades were so complicated, did you? They're not really. But it kind of looks like that. All right. So how do we do that? Well, what we do, the way that I think about it is, I get the volume of the entire solid as if it's a solid. And then I get the volume of the smaller solid as if it's a solid, and I subtract them. So it's the volume of the big solid minus the volume of the inner small solid, and that cuts it out, and it gives me the volume of what's left with the whole. Make sense? So that way it's really not anything more complicated than what we've already done. It just takes a little extra subtraction. So here's an example 9. The region bounded by the curve y equals x squared plus 1 and the line y equals negative x plus 3 is revolved about the x-axis to generate a solid. Find the volume of the solid. To me that is very difficult to visualize. To me it's like the book is even having trouble showing that. But it's this parabola and this line. And then you take that region right there and you revolve it around the x-axis. And it creates a kind of a weird shape. Okay? But what matters? Okay, what matters is, let's just take the volume of the big part. The volume of the big part is caused by this outer radius right here. What is this outer radius? This outer radius is the y-coordinates of that thing, which is just a line. It's y equals negative x plus 3. So in terms of x, it's negative x plus 3. So the volume of that would be pi. It's the integral of pi times negative x plus 3 squared dx from what to what? Does it tell me? Well, I don't know the limits of integration because it doesn't tell me, but I have to get them by finding where those things cross. I have to figure out where x squared plus 1 crosses negative x plus 3. So that's one of the things I have to do for this problem. I have to solve that equation. So let me see if that's easy to do by factoring. That's x squared plus x minus 2 equals 0. Can I factor that? Plus 2 minus 1. So x equals what? Negative 2 and positive 1. So now I know that this on the x-axis is negative 2 and this on the x-axis is positive 1. So my limits of integration are negative 2 to 1. And then I'm going to subtract the volume of the smaller region. The smaller region is defined according to this parabola right here. So what is this radius? What is this radius right here, or this radius right here, or this radius right here? It is the y-coordinate of that parabola. And the y-coordinate of that parabola, as far as x is concerned, is x squared plus 1. That's the radius of that smaller solid inside there that's getting cut out. So it's the integral, again, from negative 2 to 1 of pi times x squared plus 1 squared dx. I can't And this full thing right here will give me the overall volume of this strange thing. Did that make any sense? Kind of lost? Like, what is this? This is the volume of the solid created by revolving that line around the x-axis. So it's like if this was a full solid thing. This is the volume of the part that's cut out. So that when you take the solid thing and cut the other part out, then you get the volume that's left over, which is what we want. You could, if you wanted to think this way, you could make this into one single integral instead of two separate ones. Because the limits are the same, it could be pi times negative x plus 3 squared minus pi times x squared plus 1 squared dx. That whole cockpit thing could be integrated from -2 to 1. You could even factor out the pi from the whole thing. It could be pi times the integral from -2 to 1 of negative x plus 3 squared minus x squared plus 1 squared dx. You can do it like that. That's fine too. That's just as good, maybe even better. It's fine. You can do it either way. And when we're getting the calculator to help us with this stuff, it might be not too bad. If I were having to do this by hand, I would expand this and expand this, combine like terms, then use the power rule. Can I erase this? Anybody trying to get anything from it? Zay? Okay. I think that is enough. I think we've covered what we need to cover. And there's one more example here, but it's not really any different than what we've already done. So I'm going to leave that part. I'm going to leave it with you. And when you do your homework, as you come to stuff you get stuck on, you can ask me questions about